Hello, and welcome back to the Cosmic Companion. This week on Astronomy News with the Cosmic Companion, we are happy to be joined by Dr. Lina Necib of Caltech, talking about her discovery of a group of stars here in the Milky Way that came from beyond our galaxy. But first, we learn about active volcanoes on Venus. We take a look at the first picture ever taken of a multi-planet system orbiting a sun-like star. And we study a pair of Type 1a supernovae seen erupting in flashes of ultraviolet light. Venus is the hottest planet in the solar system, but astronomers usually thought the planet itself was geologically quiet. However, a new virtual model of the surface of that world shows that features called coronae show clear evidence of recent volcanic activity. These structures, unlike anything seen on Earth, are also clustered, potentially revealing details about geological activity happening deep beneath the surface of Venus. Roughly 300 light years from Earth, the TYC 8998 761 planetary system has at least two supermassive planets orbiting far from the central star. A new image taken in infrared light shows two exoplanets orbiting their sun for the first time. The inner planet in this system is 14 times larger than Jupiter and orbits the star at about 160 times the distance between the Earth and the Sun. The outermost world, 6 times more massive than Jupiter, circles its parent star at twice that distance, or 320 times further than the Earth keeps away from the Sun. White dwarf stars can erupt in dazzling displays under certain conditions. Some of these stars in binary systems can gather material from their stellar companions. And when this material builds up to a certain critical mass, the gas can explode into a Type 1a supernova. These events are relatively cool for stellar explosions, but a pair of these eruptions were recently seen accompanied by flashes of ultraviolet light. These frequencies of the electromagnetic spectrum usually indicate temperatures several times hotter than the surface of the Sun. Researchers are looking into the cause of these events, but it is possible that collisions or thermal mixing of material or little understood fusion activity could drive these strange eruptions. Today we are joined by Dr. Lina Necib, a postdoctoral researcher at Caltech, talking about her discovery of hundreds of stars in our galaxy that came from outside the Milky Way. This week on Astronomy News with the Cosmic Companion, we are happy to be joined by Dr. Lina Necib. She's a postdoctoral fellow at Caltech, who has recently discovered hundreds of new stars. Welcome to the show, Lina.
Thank you so much for having me.
Thank you. So tell us a little bit about your discovery and what it is that you found.
So basically what happened was that we were trying to build a catalog of stars that were born outside the Milky Way. And the reason that these stars are actually interesting is because they can tell us about the merger history of the Milky Way. Basically, galaxies form through mergers. So galaxies just like this one, you see that there is something colliding into it.
Mm-hmm.
And that's how galaxies grow in general. And it's very interesting to find like remnants of that. And the only way that we can do it is by looking at stars that actually don't have the right, you know, speeds, velocities, or than what you would expect. And this is how we can actually find out that they came from somewhere else. So using simulations and machine learning methods, we actually kind of, in simulations, we know where each star came from. So we taught a computer to distinguish the stars that are born from somewhere else versus the stars that are born in the Milky Way in our simulations. And then we kind of took that and used it on data and built this catalog. So my collaborator, Brian Ostick, who is now a postdoctoral fellow at Harvard, actually did a lot of this machine learning. And then what ended up happening is that he just one night sent me a catalog and he was like, these are the stars, have fun. And the game was like, okay, let's see what's in there in our catalog. So at first, I wanted to make sure that what I expected to be there, so for example, structures that I already know are there from previous mergers, for example, the merger of the Gaia sausage, which happened, which was discovered in 2018, was there, and indeed it was. But then there was this other structure on like top right corner of some stars that are, rotating with the galaxy. So for example, you would see them like, oh, I can't point at this. Okay. Basically co-rotating just like the sun, but also kind of merging in towards the sun. And that was a bit bizarre. And at first I thought I had a bug and thankfully I didn't. And what we're trying to do, what I was trying to do is actually try to figure out where that structure is. And basically there was about 250 stars that they were going all in the same direction, that is kind of co-rotating, but also kind of merging directly into the center of the galaxy, which is very unusual for stars like that, especially for, a whole bunch of 250 just going in that very specific direction. So what I wanted to, so basically that was kind of like the earlier thing, and like the rest of the project was trying to understand what that structure is and figure out what's happening. So the two major theories is that this structure, which I got to name, which is cool. So it's called Nyx, for the Greek goddess of the night. Either it is a galaxy that has merged just like that, basically, and these are the remnants of it, which is very exciting, or these are actually disk stars, so just like the sun and the galaxy, but like something kind of hit the disk and kind of push them into a kind of like a wave, or these kind of a bit of the same way you see ripples in the water if something hits, and these are the remnants of that. So yeah, there's still more to do, but it's very exciting.
That's incredible. So when did these stars first join the Milky Way? How do we find that out?
So we don't know exactly yet, but we'll find out soon. Because so looking at a few of the chemical abundances that we already have, we found out that these stars are actually quite old. So they would be consistent with 9, 10 gigayears or billion years old. We know that the universe is about 13 billion years old. So these are quite old. And what we're trying to do now is actually go and observe the chemical abundances. So basically, like, what are these stars made of, with telescopes. So actually, at the end of next week, we'll be remotely observing, unfortunately, with the Keck telescope in Hawaii, some of these stars to try to understand, like, when were they formed, where were they formed, and a lot of their initial environment, and then being able to try to narrow that down.
That's fantastic. And just, I mean, out of hundreds of billions of, I feel like Carl Sagan, hundreds of billions of stars in the galaxy, why was it these stars that were found, and how common are intergalactic interlopers like these in our galaxy?
Yes. So, yes, there are a lot of stars in the universe. So you kind of have to kind of subsample a little bit and look at the closer ones. Um, and there is this fantastic mission. It's called Gaia, and the Gaia telescope actually is a space telescope that was released in 2013. And the goal of this mission is to measure the kinematic properties, so basically the speed of these stars, of 1 billion stars. So that's 1% of the galaxy, of our galaxy, of the Milky Way. And this is by far the biggest kinematic catalog that we've ever had. And it's quite an incredible feat to actually end up with a catalog of that actually has the velocities of that many stars. So the ones that I looked at were actually a small sample. So we started by looking at out of that 1 billion, we only looked at the closer 7 million, which is and then running this whole machine learning to kind of try to disentangle the stars that are born elsewhere versus the stars that are actually from the Milky Way. That took a lot of effort because basically where we were looking very close to the sun, and in our very, very close neighborhood, only 1% of the stars actually might be coming from somewhere else. Most of them are born in the Milky Way out of the gas of the Milky Way. So that's why when it's like a needle in the haystack situation, you end up having a computer do the work for you by trying to disentangle some of these stars. And then out of that sample, I think we ended up with about 40, 50,000 that I had to sort through. And the way that I found that is by looking at what we call kinematic structure. So basically, I was looking for clumps of stars that are all moving in the same direction. And this specific clump was actually moving in a direction that it's a clump that I hadn't expected. All of them are pretty well cataloged, and this one is just coming out of nowhere, and you're like, what are you doing? And a bunch of stars are all moving in together. There has to be a reason, and we try to understand that.
So if this seems, so why is it that if this group of stars came into the Milky Way so long ago that they are still hanging out together into their interstellar clique? Seems like the gravitational interactions would have been so chaotic over the last billions of years. Why are they still a group? Is why I'm asking.
No, that is a very good point, actually. The thing is, so couple of things. First, the stars are pretty collisionless. So for example, like the first week of Astro class was asking the question, how long would it take for all the stars of the Milky Way, for 2 stars in the Milky Way to hit each other? And then you end up with an answer that is longer, like 10 times longer than the age of the universe or something crazy. And the reason for it is that they're actually pretty far from each other. So gravity is there, yes, and things do get disrupted, but but rather like their orbits change a little. You're right, though. It's quite surprising to have such coherent stream last a bit longer. So that actually is going to help us narrow down the difference between when those stars are born versus when they came into the Milky Way. Because if they came to the Milky Way way, way, way too long ago, you're absolutely right. They would have been disrupted, and like they would not be all of them together. So the thing is, but what I'm trying to say is that yes, that's a very good point, and you have to be very careful about that. But also that there is another limit where stars do take quite a long time to kind of lose their orbits and kind of. So, for example, if you start with a clump. If you throw a clump and then you let it kind of go into a few orbits, about 4 billion years ago, you will see like a lot of the stars as like one line in the sky. Streams are. So it's a very long process. The thing that makes this a bit interesting is that the Nix stars, for example, happen to be inside the disk of the Milky Way, so they might have gotten disrupted a lot faster. So what we're doing now is actually having simulations of the disk, and then we're throwing satellites at it from different directions and trying to understand if we can get the kind of like the right recipe of the stuff that we have today.
Interesting. So what led you to this study? Why did you start looking for these stars?
Looking for these. It's quite interesting because I was not expecting any of this. So like the goal of the initial project was to kind of create this accreted catalog to relate the kinematics of the stars, so the speed of the stars with the speed of dark matter. So basically, dark matter is 84% of the matter budget of the universe, but we know pretty much nothing about it, or at least very little. And what my some of my earlier work from 2017 and 2018 is using simulations to show that because most galaxies form from mergers like this one, these mergers actually bring in stars and also bring in dark matter. So stars that are born out of somewhere else might actually bring in their own dark matter, which actually can help us kind of, and then we kind of can reverse engineer it. So if you find stars born from somewhere else, you can kind of go back and deduce the speed of the dark matter, and that can help with the dark matter experiments that we have today. So our dark matter experiments, for example, is like these heavy, very large tons of xenon that we have underground, and we wait for dark matter to come in and then hit the xenon atom a little bit. And when that happens, some scintillation light kind of gets emitted, and that's how we know dark matter was there. We haven't seen anything yet, but in this whole process, it's very, very important to know how fast the dark matter is coming in. So that's why like this whole using the stars as a way of investigating how fast the dark matter was actually quite critical. And then we stumbled upon cool things, which is fantastic.
That's great. I love the connection to dark matter. And actually, last week I interviewed a colleague of yours at Caltech, Dr. Catherine Zurich.
Oh, yes.
Yeah,
of course.
I interviewed her last week, and she's been doing some fascinating work with dark matter.
Absolutely.
Setting up, talked about setting up, dark matter detectors with like a gram material detection.
Exactly.
Material. It's just outstanding. So it was pretty amazing that you got to work with the Gaia data. How did you get to take a look at this marvelous collection of data?
It's absolutely incredible, and I'm so glad that I did. It kind of like if like the data release feels like a party. So basically, there were events at CCA, the Center for Computational Astrophysics in New York, and a lot of different astrophysicists from a lot of different backgrounds, came in, and the data was released at I think it was like noon GMT or GMT +1. Anyways, it was like 6 a.m. New York time, and everybody was there, and everyone had their laptops. It started downloading the data as soon as it was available, and we had like a workshop, basically a hackathon for 3 days, trying to get so much out of the data all at once, and everybody was just like in the same room. And I think we were about like 40, 50 people. And it was really interesting because people were trying to, cross-match the Gaia catalog with other catalogs that they've had before to kind of get extra properties. And then all you have to do is like somebody would look up out of their computer and they were like, does anyone have a cross-match with the Sloan-Digital Sky Survey? And someone was like, I got it. And then they just hand you like a hard drive and you just keep at it. And it was the most amazing energy, and everyone was just like having a blast. Of course, my brain was fried at the end of 3 days. Like, I can't look at a computer again. But it's like, seeing that passion for like, really, it's kind of like a kid opening like a toy on Christmas, because like, there's so much data nobody has seen before. And all of a sudden, it's like a lot of these scientists who are just like waiting to see what happens. And everyone is just pulling the data and start playing with it to see what else is new. It's quite it's absolutely incredible.
Wow. Fantastic. And so lastly, you have to hit the most important question of all. Since you discovered the next stars, you got to name them.
Yes.
Why did you choose that name?
So that was pretty fun. Basically, I was on my messaging app with my longtime collaborator, Professor Mariangela Lasanti at Princeton, and we were trying to kind of figure out names. And we were like, all right, well, what can we name this? And because, for example, the previous merger is that it's called the Gaia sausage, but the actual full name, well, the alternate name is Gaia Enceladus, and Enceladus is a Greek god, son of Gaia. We were like, okay, we need like, something pretty epic, but we were like, there were so many gods in here. We wanted a goddess that actually that would actually reflect that goddesses actually can do physics too. So we started looking that up, and it was like, basically I looked up Greek goddesses, and we were kind of going through the list of names, and they were like, we're making jokes about some of them because apparently there's Nike, and we're like, we're not going to name it after shoes, but it's goddess of victory. There's Nemesis, which was like tempting, but not really.
Also a terrible Star Trek movie.
Right, so we're going through there was like an alphabetical list, and then it said Nyx, Greek goddess of the night, and we were like, this is just absolutely perfect. I thought it would fit, and yeah, we went with it, which was pretty fun.
That's great. Well, thank you so much for being on the show, Lina.
Oh, thank you so much for having me. This was really fun.
Great. And that was Dr. Lina Necib of Caltech, and we'll see you next week on Astronomy News with the Cosmic Companion.
Next week on Astronomy News with the Cosmic Companion, we'll be joined by Laurent Montisi of the Department of Geology at the University of Maryland. He is the geologist at the center of the discovery of recent volcanic activity on Venus. I would like to thank Florencia Vidal, the artist who created the new logo used for the first time on this episode. Make sure to look for more of her work at Flor Vidal Illustration. Please stay safe, stay healthy, and keep your wonder alive. If you enjoyed this episode of Astronomy News with the Cosmic Companion, please download and share the episode on YouTube, on Facebook video, or on any major podcast provider. For more details on space and astronomy news, please visit thecosmiccompanion.com or thecosmiccompanion.net.